Hi and hello to everyone. In this class, we are going to see about a binary floating point representation. We can represent a binary number using two representation. The first is single precision point representation, another is double precision point representation. We will see the theory behind it and we will solve few problems related to it. Welcome to the lecture. So before going into that, we should be knowing what is a floating point. If you take the decimal number such as pi, e for exponential, their corresponding decimal values are 3.14159265. Then for exponential it is 2.71828. Okay, and you can see a very small value, that is 0.000. You can see 9 zeros, 1 followed by 1, right? It can be represented as 1.0 times 2 to the power minus 9. Okay, and a very large number, you can see 315576 followed by 4 zeros. It can be represented 3.15576 times 10 to the power 9. Okay, so the point here is we can represent a very small number as well as a very large number using the representation raising it to the 10 to the power exponential values. Okay, right? So these sort of why I am using 10, because we are dealing with decimal numbers. Okay, these are all for the decimal numbers. Similarly, we can see in a computer arithmetic we will be representing number in which the binary point is not fixed, right? Okay, that's why we say these are called as binary point or floating point, right? Okay, so we'll see the two ways to represent. The first one is the single precision. What is a single precision? The floating point value represented in a single 32-bit word. Okay, that's a floating point number. We can represent using 32-bit word, right? What is a 32-bit word? So this is the 32-bit word. You can see here I am starting from 0. The next bit is named as 1, going up to 31. The representation is like this. Okay, the most significant bit is assigned for the sign bit, which is given the value, 1 bit is assigned to it. Then the next 8 bit is assigned for the exponent. Then the rest of the 23 bits is assigned for the fractional part, right? This is the format for single precision. Okay, for single precision we will be using how many bits? 32 bits to represent, right? Okay, now using the single precision we can represent a number very small as 2 times 10 to the power minus 38. Okay, 10 to the power minus 38. You can see I am using a suffix 10 to represent these are decimal numbers. A very small decimal number such as 2 times 10 to the power minus 38, as small as this value, and it can be as large as 2 times 10 to the power 38. Very large value. This range can be represented using single precision. Okay. Normally it's not possible, right? If you are using the entire 32 bits to represent the magnitude, this range is not possible. Okay, you have studied about the 2's complement representation. In that, one among the 32 bit, 1 bit is assigned for the sign bit, rest of the 31 bit is assigned for the magnitude, right? Using that, you cannot even have this smaller range or this very large value. Okay, that is the reason why we go for single precision. And what about the double precision? In double precision, we are using two 32 bits, two 32-bit words. Okay, you can see here I am using two 32 bits. This is 0 to 31, 0 to 31, right? So this 32 bit I name as a word. This 32 bit I name as a word. So I have two words. Okay, this the most significant bit is assigned for the sign bit, and this 11 bits, that's a bit 21 to 30. The 11 bits are assigned for the exponential, and the 0 to 19 bit, that is a 20 bits assigned for the fraction, and this entire word is assigned for the fraction. Okay, so this 32 bit along with this 20 bit together 52 bits is assigned for the fractional part. Okay, right? So this is the representation of a double precision. If the double precision means you need two 32 bits, that is 64 bit to represent the double precision. So obviously the advantage would be the more precise values, like a very small number, that is 2 times to the power of minus 348. very small values can be represented, as well as a very large number 2 times to the times 10 to the power of 308 can be represented. Okay, this large number and very small number. Okay, of course, when you compare with the single precision, you can clearly understand in single precision it's 2 times 10 to the power of 38. Okay, that's the largest value possible. But here you can see 2 times 10 to the power of 308. It's a very large value. Okay, so that's a advantage of going for the double precision. Of course, you need another 32 bits. Okay, and these single precision and double precision are all coming under the IEEE 754 floating point standards. Okay, now we take a problem. We'll do the single precision 32 bit floating point number for the given decimal number. The decimal number is minus 0.75. Okay, the base 10, this is the base 10 to indicate it is a decimal number. I want to represent this number in single precision 32 bit floating point number. Okay, now what are the steps I'm going to do? First thing, you convert this 0.75 into binary number, right? How to convert this decimal, the fractional part, right? This 0.75 into binary. The thing is, you have to keep multiplying by 2, and you have to split this into like 0.75 into 2, which is 1.5. This 1.5 I can write as 1 plus 0.5. Okay, next I have to again take this fractional part, which is 0.5 times 2, which is 1.00, so I can write this as 1.0.0. Okay, now I have to take this number, this 1 and this 1, right? So this number I have to write it from the top, 1.11. So 0.11 is the binary representation of 0.75. That's the first step, right? Next step, we have to normalize it. That is the 0.11, which is in binary, is represented in the normalized format. What is normalized format? That is, in the left side of the binary point, you should have only 1. Okay, so we have 0.1 is here. So we want to move this point. That is a binary point, to this position. Okay, see, I'm going to, yes, you can see here I am moving this point to this position. Okay, so since I am moving towards the right, each digit if I move, I am going to the 2 to the power is raised to minus 1. Okay, I am moving towards the right by single digit. Okay, so I am raising it to the 2 to the power minus 1, right? If I am moving to 2 digit, it should be 2 to the power minus 2. I can also give some example related with this. You can see, suppose if the number is like this, right? How can I normalize this? I should bring this decimal, this binary point to this position. Okay, how many digits I am moving? I am moving 3 digits to the right. Okay, so it is 1.1 2 to the power minus 3, right? And I can give some other example like 1011.11. Okay, how can I normalize this? It should be in, what is normalization? It's like it should be in 1 point, you should convert 1 point something, right? So you can see here the dot is here, so I need to bring the dot to this position, right? So how much I have to shift it to the left to the 3 digits, right? So this is converted to 1.0111. Okay, how many digits I am moving to the left? 3 digits, so it is 2 to the power 3. Got it? Okay, yes, if you can understand this, then we can move into the next step. So we have normalized this. Next step, we know the fractional is represented. This is the fraction part. This 0.1 is the fractional part, right? So try to write, after normalization, try to write 0.1 in 23 bits. Because we have seen in a single precision point, the fraction is required to represent it in 23 bits, right? So represent that in 23 bits. So 1 followed by, I am putting 22 zeros. Okay, this fraction is also called mantissa. Okay, then there is something 2 to the power minus 1, right? This minus 1 you represent by the notation e, right? So how you compute the exponential? Exponential is nothing but the bias plus e. The bias in single precision point representation is 127. You keep in mind that the bias is 127. So e in this case is minus 1. So 127 minus 1, which is 126. Okay. Now convert this into binary. How many digit I have to convert this into binary is very clear. If you can see, the single precision point needs the exponential to be in 8 bits. Okay, so you have to convert that 126 into 8 bits, right? How will you convert 126 into binary? That is by repeated division. Okay, keep dividing and write the remainder next to it, right? So it is 63 times 2 is 126, the remainder is 0. 2. 36 times 2 is 31. 31 times 2 is 62, the remainder is 1. 15 times 2 is 30, remainder is 1. 7 times 2 is 14, remainder is 1. 3 times 2 is 6, the remainder is 1. 1 times 2 is 2, remainder is 1. Okay, so we have to write it from this bottom to the top. So it is 1 1 1, 6 ones followed by 0. 6 ones followed by 0. We can see 6 ones followed by 0. Since we need represent in 8 bits, I am adding another 0 here. So totally the exponential is converted, that is 126, the decimal number is converted to binary number. Okay, right. So we got the fractional part, we got the exponential part. Fractional part is of how many bits? Fractional part is 23 bits. Exponential is how many bits? 8 bits. Okay, then what about the sign bit? Look at the question. The question is minus 0.75. Minus is a negative sign. So the sign bit is 1 for the negative number. The sign bit is 1. If the negative number, the sign bit becomes 1, right? If it is a positive number, the sign bit is 0, right? In this case, a negative number. So I can fit everything. So this is my sign bit. This 8 bit is my exponential. This 23 bits is my fraction or mantis, I can say. Okay, so this is the 23 bits, 8 bit, 1 bit, totally 32 bits. This is the single precision point representation of the given number, which is minus 0.75. Okay, now we move to the next one, which is 24.85. This number we are going to convert it into single precision point. Single precision 32 bit floating point number. Floating point number. We want to convert this 24.85. What is the first step? Quickly we can do. First step, convert this 24.85, which is a decimal number, to binary. How will you convert? Take the 24, keep dividing by 2. 12 times 2 is 24, remainder is 0. 6 times 2 is 12, remainder is 0. 3 times 2 is 6, remainder is 0. 1 times 2 is 2, remainder is 1. Okay, write it in this way. So the 24 is represented as 11000. Keep the dot, binary dot. Then what about 0.85? 0.85 can be converted to binary by repeated multiplication, right? So 0.85, if you multiply by 2, which is, we will get 1.70. Okay, so I can write this as 1 plus 0.7. Take 0.7, again multiply by 2. Okay, so 0.7 multiply by 2, which is 1.4. Write it as 1 plus 0.4. Again take the fractional part, 0.4 multiply with 2, which is 0.8. You can write this as 0 plus 0.8. Take 0.8 multiply with 2, which is 1.6. 1 plus 0.6. take 0.6 multiply with 2, which is 1.2, which is 1 plus 0.2. Take 0.2 multiply with 2, which is 0.4, which is 0 plus 0.4. Okay, 0.4 multiply with 2, which is 0.8. Okay, 0.8, which is 1, so not 0.8, yeah, 0.8, which is 0 plus 0.8. So 0.8 multiply with 2, which is 1.6, which is 1 plus 0.6. Okay, so again it is repeating. You can see here 0.8, you can see here 0.8, 1.6, 1.2, 0.4, 0.8, 1.6. If you keep going, it is 0.6 times 2, which is 1.2. So it is 1 plus 0.2. Again 0.2, take the fractional part, 0.2 times 2, which is 0.4, which is equal to 0 plus 0.4. This keeps on going. So what we can do here is, you have to take this 1 1 0 0 1 0 0 1 1 0. You can see a pattern, right? What is a pattern? What is a pattern it is repeating? If you see it clearly, 0.8, 1.6, 1.2, 0.4. Again 0.8, 1.6, 1.2, 0.4. Okay, so this is the pattern. This is one set, this is one set. Okay, so how it is repeating? 0 1 1 0 0 1 1 0. It's keep on going like that, right? So if you can write from the top, the first, okay, right side of the binary point, it is 1. So put 1 here. Then the next digit is 1. Put 1 here. Okay, then it is 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0. It keeps on going, right? Okay, right. We have to write for at least 23 bits. Okay, right. Now this step is done. We have converted the 24.85 to binary, the base 2. Okay, the next step would be, we have to normalize. What is normalize? If you see here, the decimal point is here, sorry, the binary point is here. I need to bring this point to this position. Okay, right? So how to normalize? I can write this as 1.1000, then 1101 1001. Okay, just I am rewriting this, right? You can see here 1000 1101 1001 1001. Okay, this part is done. Then this part is done. Then we have 1001. Okay, I have to write for 23 bits, right? How many bits I have written? You can see here in the fractional part, 4 4 4 16 I have written. Okay, then another 4, then another 3 bit, right? Okay, so this number is converted to this. How many digits I am shifting my binary point to the left? I am shifting to the 4-bit position, right? So it is 2 to the power plus 4. 2 to the power plus 4. If I am moving to the left, it is to the power 4. If I am moving to the right, it is minus 4. Okay, I am moving to the left, so it is to the power 4. Now, what is this? This is the fraction, or I can say mantissa. This 4 is the E. Okay, right? Now in the next step, what I have to do, I can convert, I have to find the exponential. The exponential is equal to bias plus E. What is bias? Bias is 127 for single precision point. E is 4, which is 131. Convert 131 into binary. Write it in 8 bits. Okay, 131 into binary, right? So what is this? This is 65 times 2 is 130, remainder is 1. 32 times is 62 is 64, remainder is 1. 16 times 2 is 32, remainder is 0. 8 times 2 is 16, remainder is 0. Then we have 4 times 2 is remainder 0, 2 times 2 is remainder is 0, 1 time 2 is remainder 0. Okay, right? So write it from the bottom to the top. What we have here, this 131 is represented as 1 5 zeros followed by double 1, right? Okay, so 131 is converted, the decimal is converted to 100, right? 100 doubles 100 0011. So this is the exponential, right? Now we are going to write the answer in a single precision point. What is the answer? The sign bit. The given question, if you look at the question, it is a positive number 24.85. So the sign bit is 0 followed by exponential. What is exponential? 1000011 followed by fraction. What is the fraction I have here? Yeah, this number, this entire thing will be coming here. Okay, so the fraction is 100001101 1001 1001 1001 and 100, right? So this entire thing is the fraction. How many bits? 23 bits. This 8 bit is the exponential. This 1 bit is the sign bit. Okay, this 32 bit representation is the, what I can say, it is a single precision point 32 bit representation of the given decimal number, which is 24.85 is converted to this, right? Okay, I hope you got an idea, right? Okay, thanks for listening. See you soon. In the next video I will be solving the double precision point problems. Okay, thanks for listening. Thank you.